Okay, we are going to talk about water today. So this is chapter 2, which is all about water. So we need to revisit and make sure that we remember some of the background about water and the chemistry of water, because we're going to apply that a lot to what we're talking about in biochemistry. So let's just talk about water for a second. So water is H2O. If we were to draw the Lewis structure of water, so remember a Lewis structure, the valence electrons, hydrogen has 1 valence electron, and I have 2 of them. Oxygen has 6 valence electrons, which means I have 8 total electrons. So I'm going to put the oxygen in the middle. I'll draw a bond to each hydrogen. So that's 2, 4, 6, 8. So that is the Lewis structure of water. Remember, the Lewis structure is just a skeleton of how the atoms are arranged and where the electrons are, but this is not the actual shape of water. So what we need to do is we need to apply electron pair geometry and molecular geometry to this. So remember, the electron geometry of a molecule only cares about the regions of electrons around that central atom. And remember, we call this the steric number. So the steric number of water is 4 because there are 4 regions of electrons around this central atom. 1, 2, 3, 4. So that means the electron pair geometry of water is tetrahedral. And if you remember that a tetrahedral molecular geometry in 3 dimensions has angles of about 109.5 degrees. So remember, the difference between electron geometry and molecular geometry is that electron geometry just cares about the regions of electrons. It doesn't care if that region is a bond or if it is a lone pair of electrons. The molecular geometry does care. So the molecular geometry of water, because there are 2 bonds and 2 lone pairs, it is going to be bent. And if we were to draw it, remember this is in 3 dimensions, we would have lone pairs up here and hydrogens down here. So because these lone pairs up here take up more space sterically, it decreases this angle between these 2 hydrogens. So this angle between these 2 hydrogens actually ends up being about 104.5 degrees. It's decreased because when you have a molecule with lone pairs of electrons, these lone pairs of electrons take up more space, which leaves less space between these 2 bonds. It decreases the bond angle. So water is a bent molecule, and it has a bond angle of about 104.5. Another important characteristic of water is its polarity. So remember, when we're talking about polarity, we're talking about a difference of electronegativity. We're also talking about if there is an overall dipole, or you might have learned it as a net vector. So remember, polarity, if it has a partial positive charge, this would be less electronegative. And if it had a partial negative charge, it would be more electronegative. So you might see something like this, these lowercase delta signs that look kind of like a S and an 8 without the 8 closed right here. This would be partially positive. And this would be partially negative. Biochemistry uses nomenclature and symbols from both biology and chemistry. So if you're ever looking at a picture in the textbook or in a PowerPoint and you're struggling that you don't understand what one of the symbols means, just ask, because sometimes it's implied and assumed that students know what all of this means, and if you don't, that's totally fine. Just ask. So if I was to assign what was happening here, so I know that oxygen is more electronegative than hydrogen. So that means that up here it would be partially negative and down here would be partially positive. If you were to draw the vectors on here, remember it points towards the more electronegative and away from the less electronegative. So the vectors would look like this. These are the vectors of the bonds, and then to see if the overall polarity of the molecule, you add them together. If you added these two vectors together, you would get an overall net vector in this direction. So this is how we know that water is a polar molecule. These partially positive and partially negative charges, you're going to see these when we start looking at big protein structures. You're going to see these little positive and these little negatives all over the molecules that are helping the molecule keep its shape. And this is where it comes from. So this is all the way back to what we know about water and Lewis structures, molecular geometry, all of that from general chemistry. So water is a polar molecule. So now we classify pretty much every molecule or chemical into two categories. So it can either be hydrophobic or hydrophilic. And again, like most things in science, the name tells you the definition of the term. So for example, hydrophobic, hydro means water, phobic means fear of. So anything that is hydrophobic is going to be non-polar, because remember, polar things only like other polar things. So if it's non-polar, it is going to be hydrophobic. So for example, oil and water do not mix because water is polar and oil is an example of something that is non-polar. So hydrophilic molecules would be polar. So we're going to talk about this a lot later when we talk about non-covalent interactions. And we're going to call these van der Waals interactions, this hydrophobic, hydrophilic. So we'll come back to this later, but this is important. Water is polar. It's polar because of the shape of this molecule and the electronegativity of oxygen and hydrogen. And this is going to set up everything, because water is what we call the universal solvent. Most things, especially chemical reactions happening in our cells, are in an aqueous environment. So we're going to find that molecules will fold or kind of organize themselves so that the hydrophobic parts of molecules are going to be tucked inside that molecule, kind of away from the water. And then the hydrophilic parts of the molecule are going to fold so that the hydrophilic parts are exposed to the water because they like water. So this is one of the first important things about water, is the hydrophobic, hydrophilic interactions that we're going to see. Another really important thing about water is its ability to hydrogen bond. So water has an opportunity to hydrogen bond in two places for every molecule of water. So we'll just draw this molecule again. So here's water. And remember we said that a hydrogen bond is between a hydrogen that is covalently bonded to either an oxygen, nitrogen, or fluorine, and another oxygen, nitrogen, or fluorine. And we will just use oxygens as examples here, but we will see examples with nitrogens later. When we talk about DNA and protein, we'll see that nitrogens also can do this, but we're just going to use oxygens here. So this is just a special example of a dipole-dipole interaction. It's stronger. It's only for oxygens, nitrogens, and fluorines. So what happens is that the lone pair of electrons on here, they act as acceptors, and the weakly acidic oxygen hydrogen bond here, it acts as a donor. So if I were to draw another water molecule here, what we would see is that there would be a hydrogen bond between the hydrogen of this water molecule and the oxygen of this water molecule. So there's two important things that are happening here. The hydrogen bond is between a hydrogen and an oxygen. This hydrogen must also be covalently bonded to an oxygen or a nitrogen or a fluorine, but in this case it's an oxygen. So water has two places to hydrogen bond, and we're going to see that that really contributes to water's stability, both in molecular structure and also in its ability to resist change in temperature, which is going to be really important. So structure of water, ability to hydrogen bond, very important. We'll talk a lot about non-covalent interactions later, and both this hydrophobic, hydrophilic is a non-covalent interaction, and hydrogen bonding is a non-covalent interaction. The third non-covalent interaction that we probably won't mention in this chapter, but we'll see later, are something called salt bridges. Salt bridges, remember the word salt in chemistry just means an ionic compound. A salt bridge would just be an ionic interaction between a positive ion and a negative ion. Those are the three non-covalent interactions that we'll come back to later. Let's see. So, because of the hydrogen bonding, it causes water to be very stable. And what I mean by being stable is it has a very high specific heat, a very high heat capacity, which means you have to put a lot of energy in to change the temperature of water. So there are some slides in the lecture that talk about boiling point, melting point, heat of vaporization of some similar molecules, and you'll see that water by far has the highest of all of these thermodynamic values. This is because the hydrogen bonding increases the stability. So you have to add more energy to change this little triangle here, delta means change, to change the temperature of water. So it has a really high, what we call specific heat, or in the chart it says heat of vaporization, which would be changing the phase from a liquid to a gas. This is really important for living things. If you think about lakes and bodies of water, you can have a temperature change in the air of maybe 20 degrees some days, where it is colder in the night and then warmer in the day, but the temperature of the water stays the same almost all day. This is important for things living in the water. Also, another important part about water is that because these hydrogen bonds increase the stability, water is one of the few substances, it's not the only substance, but it's one of the few substances that is actually less dense as a solid. Because the lattice structure of these hydrogen bonds, it actually expands. And you all know this because you know if you put an ice cube in a glass of water, the ice rises, it floats on the top. Or if you've ever tried to freeze something that's totally full of water in your freezer, it will explode because that ice is going to expand as it freezes. That's because the lattice structure of these hydrogen bonds between all these water molecules will actually expand as it goes from a liquid to a solid. Water is not the only substance that does this. it is the only one that we will talk about. Most solids are more dense as a solid. And another important property of water relating to this is that lakes and bodies of water freeze from the top down, not from the bottom up. So when a lake freezes at the top, it freezes, and then the water at the bottom still stays about the same temperature. This is called lake temperature stratification. And the fish and the life in the lake are all still able to exist during winter. If water was more dense as a liquid and it froze from the bottom up, it would freeze solid, and there would be no life in any bodies of water in the winter. So this is another really important property of water. We will stop here, and then next I'm still going to talk about water, but I'm going to talk about pH. We'll do a little bit of review of pH and how that is going to apply to biochemistry.